Let's talk about a number, how it is stored on a computer as a floating point number. Which number should I use? Please tell me one number. Okay, let's assume you tell me this number. It's a very good choice because in this case it will not take too much time to find the solution if it was some. Okay, let's start. What is the first thing? The first thing is let's check if it's a positive number or if it's a negative number. It's a positive number, so the sign bit is 0. If it was a negative number, the sign bit would be a 1, because it's -1 to the power of 0 is plus and to 1 would be minus. Now, what is the number we are looking for? 2 to the power of 0 is 1. 2 to the power of 1 is 2. 4, 8, 16, 32, and then 64. 64 is the correct number because the next power will be more than 71. So 2 to the power of 6. And we have to write it that way. So which is the number we have to use? 6 more than that. So we have to encode it as a binary number, so we again need the powers of 2, which are 1, 2, 4, 8, 16, 32, 64, and so on. The last available number for a 64-bit number is 1024. And we need that 1024, then 5 are left. Let's write the 5 as a sum of powers of 2, so we need 4 and 1. And now we have written this number as a sum of powers of 2. And that means we used a 1024. We did not use a 512. We did not use a 256. We did not use a 128. We did not use a 64. We did not use a 32. We did not use a 16. We did not use a 8. We used a 4. We did not use a 2, and we used a 1. So this is the binary representation of this number. Now the third step, we have to divide by 64, and then this is the logic. So now our job is to find the representation of that number. Using an electronic calculator, it tells me that this is the decimal representation of that number. Let's write a 10, that it's a decimal number. And now we want to write that number in the binary representation. So it's 1 point and then some zeros or ones are following. So what to do? Let's take that number and let's subtract 1. And now our first step is, let's check if we have to use the first digit after the dual point. If we would use 0.5, it would be too much, so don't use 0.5. So we check a half, which is 0.5. This is more than this number, so we don't use that. And that is what we have done. And now we know the first digit after the dual point is a 0. And let's continue that way by checking the negative powers of 2. And let's do so. Is this number less than that number? No, it's not. So we don't use 1 divided by 4. And we have here the second digit. Let's continue with 1 divided by 8. This number is more than that number, so we again don't use it. And now for the first time we are in the situation this number is less than that number, so we use this part. And now we subtract these two numbers. Let's subtract from that number this, and you get 0. Then we continue with 1/32, which is this number is less than that number, so we use it. I forgot to write that down. And now again, we subtract from that number the number we have used, and so we get, and again, this number is less than that number, so we have to use 1/64, and again, subtract these two numbers. And again, this number is less than that number, so we have to use, and we have to subtract. And now this number is more than that number, so we don't use 1 divided by 256, and we continue with that. And in this case, these numbers are identical. Okay, so this number is less or equal to that number, so we use a 1. If we subtract these numbers, we get a 0, and that means that continuing that process, nothing will happen apart from zeros. So we have that, and now we have 3 parts. Our first bit, these 11 bits, and these 52 bits and zeros following. Now the job is done. The sequence of bits is stored on your computer, but for better reading purposes, in MATLAB in Octave, we do not display these bits, but we pack them together in groups of 4 and build a hexadecimal digit. So this is 1, 2, 4, 8. So this is a 4. This is a 0. This is a 4 and 1 is 5. This is a 1. This is a 8 plus 4 plus 2, which is 14. And in hexadecimal writing, it's an E. And this is a 8, and zeros are following. So we have found what we've been looking for. Let's check in MATLAB. And what do we see? A 4051 E8 and zeros following. And that is what we have found out. So storing this number as a floating point number, this sequence of bits will be saved on your computer. Okay, this is step 3, and this is essential for understanding what's going on. But then there's an alternative, and I also want to show you this alternative for step 3. This is the idea, and I will show you. Okay, so what to do? The process till here is the same, and so here is the starting point for the alternative. We have to check if this number is less than a half, then we don't use a half, or if it's more than a half, then we will use it, and then we will get a 1 here. And how can that be done? Alternatively, we can multiply this number by 2, and then we can check if this is more or equal to 1, or if it is less to 1, and that's what we do. So multiply with 2 and check if it's more than 1. It is not, so let's use a 0. Then multiply by 2 and check if it's more than 1 or not. It is not. Multiply by 2 and check if it's more than 1 or if it's not. Then multiply by 2 and check if it's more or equal to 1 or not. In this case it is, so let's use a 1. Now subtract 1, that is what we did here. Using it, we will subtract something, and now we subtract in this case 1. multiply by 2, and check if it's more than 1. It is. Okay, then subtract 1, multiply by 2, and check if it's more or equal to 1. Yes, it is. So use a 1, subtract 1, multiply by 2. It's more than 1. Okay, subtract 1, multiply by 2, and check if it's more or equal to 1. It is not. Multiply by 2, check if it's more or equal to 1, subtract 1, and now if we have a 0, we will multiply by 2, check if it is, and so on. So zeros are the numbers continuing, and so we get here this sequence. It's 0, 0, 0, 1, and so we also found out that. So that's the way it works, either this way here or that way. Let us discuss a second example. Let's discuss minus 0.1. In this case, this number is negative, so the sign bit is 1. Now we have to find the largest power of 2 less than 0.1. And what is that number? That's too much. 0.5 is still too much. 0.25 is still too much. 0.125 is too much. And this is the power we need, so it's the minus 4. Now let's write minus 4 as something minus 1023. What do we need? We need 1019. Okay, and now we have to find the binary representation of 1019. The first bit is the 1024 bit, and we will not use this in the sum. 512, yes, we will use, and if we subtract what is missing, then we get 507. That plus that is that. So 256, yes, we use it, and then let's subtract, so we get 251. Yes, we use it because it's less than that. So what is missing? We use 64. What is missing? 59. We use 32. What is missing? 27. We use 16. Missing 11. We use 8. Missing 3. We use 4. No, we don't. We use 2. Yes, we do. We use 1, 0. Okay. So what is the binary representation? 1029 is written in binary code 0 times 1024, 1, 1, 0, 1, 1. Third step, 0.1 divided by this largest power 2 to the minus 4. This is 1 over 16, so 0.1 divided by 1 over 16 is 16 times 0.1, so 1.6. So let's write 1.6 as a binary number. 1 point, what is missing? 0.6. Do we use a half? Yes, we do. What is missing? 0.1. Do we use 0.25? No, we don't. Do we use 0.125? No, we don't. Do we use? Yes, we do. What is missing? 0.0375. 0.03125. Do we use? Yes, we do. And so on. So what did we find out? 1, 0, 0, 1, 1, and some more digits. what did we find out? So this 1, then this sequence, and then that sequence. In hexadecimal code, 8 plus 2 plus 1 is 11. 11 is a B. This is 15 F. This is B. Again, this is 9, and this is something more than 8. Okay, so this is our result. This sequence is stored on your computer, and if you ask MATLAB how minus 0.1 is stored, then he will tell you BFB9, what means this is the sequence. So these were our 2 examples, and now it's your job to do another example, and then I think it's not too hard to understand.